Good morning, colleagues and students, and welcome to today's Faculty of Engineering and IT Research Excellence Distinguished guest lecture. And this lecture today also co organized by the Australian Academy of Technological Science and Engineering, (ASSE). My name is Professor Long Yim. I'm the director of the Center for Technology in Water and Wastewater here at FEIT, and I'm the MC on behalf of Professor Ji Lu, distinguished Professor Ji Lu, who is our Associate Dean Research Excellence of the faculty. And before I comment, I would like to acknowledge the Gadigal people of the Eora Nation upon their ancestral land. Our UPS campus now stand. We pay respect to their elders, past, present, and emerging, and acknowledging them as the traditional custodian of this land. Today is an absolute pleasure to introduce our guest lecture. This is the 15th Research Excellence event in 2025, hosted by FEIT. And since the program began in 2017, we have been hosting the Research Excellence lecture series and training events, and this is also the 67th distinguished guest lecture that we have got since 2017, which is by now 8 years ago. And it's an absolute pleasure to introduce our guest speaker today, Professor Menachem Elimelech. We call him Manny for short, and I'm sure Manny is happy for everyone to call him Manny. And Manny is the Nancy and Clinton Carson Professor at Rice University. Many have been elected to the U.S. Academy, the U.S. National Academy of Engineering, and in 2021, many have also been elected to the Australian Academy of Technological Science and Technology as a foreign fellow. And with a footnote that only one foreign fellow can be elected in a year. So it is an absolute pleasure for us to have today guest lecture by Manny. He have advised to completion 55 PhD students, and somehow I'm also included in that number, some included actually. And many have also advised 54 postdoc fellows. So he have left behind a very, very big tree of academia knowledge. So many, without further ado, I'd like to invite you to the stage, and everyone here in the room, as well as people online, are really looking forward to the lecture. Thank you.
For the kind introduction. I'm really happy to be here. The second time at UTS. Last time was way before COVID. I mean, I don't remember the year, but at least 7 to 10 years. Okay. So anyway, today I'll talk about the critical metal recovery, and more specifically about the role of membranes. And I know it's a hot area nowadays. I heard also that Trump, the Premier of Australia, signed an agreement about critical metals, so maybe it will be quite relevant to Australia. So. So it doesn't move yet. Okay, it still doesn't move. I think it was something gets stuck. Okay, great. So again, after more than 25 years at Yale University, I moved in January to Rice University. Again, we are part of the Rice Water Institute, and we also have a Center for Membrane Excellence. And those of you who are not familiar with Rice, it's in the great state of Texas, in the Houston area that you see here, close to the Gulf of Mexico. Okay, so anyway, there is a need for selective processes to recover metals, and again, there could be a wide variety of metals. Again, these are just some examples. You can have electronic ways in which you can recover very, very important minerals, and I'll talk about them later. You can think about lithium-ion battery recycling. You can think about resource recovery from wastewater. And you can think about lithium brine extraction that we also hear a lot about. Now, okay, so let's take some example. Again, renewable energy relies a lot on the availability of critical metals. For example, in lithium-ion batteries, we need a lot of lithium and nickel and cobalt. And for renewable energy by, again, solar, we need some other elements that you see here. So we need a perpetual supply of these elements. Now, recycling also can increase the long-term supply of these critical metals. Let's try to see, get rid of this over here. Okay, and currently we recycle very small amount of metals, only about 34%. When it comes to iron and steel, we have very high recycling rate, but not a lot for the other metals. And of course, the key for recycling is really to preserve our natural resources. Again, mining is very unfriendly environmental process, so we want to avoid it as much as we can. As I mentioned, it's become important for many countries all over the world. And again, this is, for example, a call for proposal that was a few years ago from the US. And now we have another call for proposal for much more money on critical metals, because they're very important for national security, as you see, again, in many other countries. So generally, again, our goal is really to recover them from different water sources. And a lot of technology were proposed to recycle these metals from different water sources. But unfortunately, there is little guidance of what metals may be technologically and economically viable for recovery. So we need to have some better way to assess this viability of metal recovery. And again, a few years ago, we have written a perspective article that you see here, that we set some rules about the recovery of these metals, and I will give you just the highlights of this article. Again, the question is which metals are worth recovering. So several governments, including Australia and European Union, have a list of critical metals that imported from their countries or their organization. And this is, for example, again here, you can see the 5 government and countries, US, EU, Japan, Australia, and Canada. And each one of them is a huge list of minerals. But when you look at the intersection, what's common to all of them, you see a very large list of minerals. So again, it's very difficult based on this definition of critical metals for each country to decide which metal to recover. And you see that, again, it doesn't work this way. Again, let's ask farther. There is also a list of what we call companion metals. And companion metals are very important metals that are recovered as a byproduct from another metal. They are not recovered just alone, they are part of another metal. So you recover other metal, and then you recover also these companion metals. And this is graphed from this article that we produced, that you have percent of metal obtained as a companion, and this is the functional recycling rate. Okay, so when you see here at the upper again corner here, we see minerals that have very high level of companion, and also very little recycling rate. So you can say that at least for this one, it will be viable to recover them, because again we have very little recycling rate, and they are very obtained only as companion. And when you look at this list, again, these numbers here, I'll just tell you, if it's 0, it means it doesn't belong to any of these 5 governments that I mentioned, that the critical metal. This blue belongs to one of them, and here, this shape, whatever you call it, belong to all the 5 metals. So when you look at this list, you see that in this upper corner, we see gallium, germanium, and you see some of these rare earth elements that you see here. So you can say, at least if we follow this definition of companion metals, probably it's better to recover this one, because again, they are very low recycling rate, and also they're obtained mostly as companions, so it's very difficult to obtain them. And I say obtain as a companion when you mine them from the ores in the underground. Okay? Now, metals, you can think also, maybe we should recover all the metals that are used in renewable energy technology, because again, it's very important for each country to develop renewable energy. And again, if you look at this definition, it will be lithium, cobalt, and nickel. They are used a lot in batteries. Or all these metals that you see are including some rare earth that are imported for renewable energy by solar method. Now, a very important criterion when you recover metal is the price, the market price, and the concentration of this metal that's available in these water sources. And here we compiled a Sherwood plot. Again, Sherwood plot is very common in chemical engineering, that you present the market price versus concentration, and usually you present it as a decreasing, decreasing concentration. And this will give you some idea about the viability of recovery. So let's look, for example, here. If you look at gold, you see gold, it's a very, very low concentration and very, very high market price. So when you look at gold, again, if you look at this analysis and you do further process engineering, it will never, ever be viable to recover gold from the ocean, and I will show you some calculation, because whatever you do, you need to filter. It takes so much water, even if you have the most selective process, it will not be viable. So don't try ever to recover gold, because it will be, not economical. So the recovery difficulty, again, can be estimated from the concentration of metal in water. And as you see here, for example, calcium, magnesium, they are very, very high concentration, as you see here, and probably they will be very viable to recover. And I will talk about it in a few slides. So remember, Sherwood plot is very, very important. And anyone who took a separation class in a chemical engineering curriculum went through this very famous Sherwood plot. Now let's talk about more about the economic viability of metal recovery. So let's take an example, lithium. So to be economically viable, again, let's read this more textbook definition, and then I will break it down. The metal market price must be greater than the levelized cost of water processing divided by the metal concentration. In a way, if we have the market price, again, we need to extract it in a way less than the market price. And this is described by the levelized cost of water processing, in a way how much water we need to process through this separation process. And here I will show you some calculation based on really assuming that once you process the water, you get 100% efficiency of recovery. So this will give you the upper case that you will never do better than it. And we can construct this graph based on this simple equation that here we present here for the lithium, for example, the lithium price. Again, usually you have lithium in lithium carbonate versus the concentration. Here we have two graphs, concentration up to 1 milligram per liter, and then another one with higher concentrations. And in the shaded area that you see here, this is the current, again, when we wrote the article, was the current price range of lithium. I think now it's about $10, $12 US dollar per kilogram. And here we see these price lines, 0.01 cubic meter per cubic meter, 5 cents and $10. Now, we look at seawater. Look at the seawater. This is the concentration of lithium in seawater. Then you go down to this curve and you see where these lines intersect with the current price. So I tell you, in seawater, to be economically viable, even if you have the process that is 100% selective, you need to process the water in about less than about 1 cent per cubic meter, just to process the water, pump it through your separation process. And you already see that it will not be impossible. 1 cent per cubic meter, again, you cannot find anything. And considering that you need also to separate it, it's not under efficiency, it will never be economical to recover lithium from seawater, including brines from desalination plants, which are only twice as much concentrated. Now let's go farther. In battery manufacturing, if you develop a process, the concentration can be all the way to 1,000 to 2,000 milligram per liter. And if you look here, it should be milligram per liter. Okay. So when you look here, this is the range. So it intersects, again, this is the price, intersects about $50 per cubic meter, and then it's reasonable. You can process 1 cubic meter in $50 with the pump and all the process. So I tell you that here it will be quite economical. And let's take an example. There was a paper indicating that extracting lithium from the Salton seeds in Southern California, it's a very high salinity sea or whatever you can call it there. They report 200 milligram per liter lithium and $4 per cubic meter. And when you go to 200, you see that we're roughly intersecting around the $5 per cubic meter, in the right range. So I tell you that there maybe it will be economical. Let's take another example. a metal that is scarce, not very high concentration, and gallium is a good example. If you look again at the same graph, the gallium concentration in seawater is here, very, very low. And this is the market price. And it tells you here, if you go here, it goes to, you need to process the water with the prices 1 10 to the minus $5. Again, you cannot even find it any coin like this. So this will never be economical, whatever, if you take brines. However, if you go to semiconductor, wastewater, about 35 milligrams per liter, so it's very, very high here. You can go and it takes about $10 per cubic meter to process, so it may be viable there. So again, in this industrial wastewater. So go now to the key conclusions here. So I want to move it here. The key conclusions from our study is that for most elements, except calcium, magnesium, potassium, and sodium that are very high concentration, it will not be viable to recover them from seawater or any natural water. And when I say seawater, including seawater brine, and we need to go to industrial wastewater that have very high concentrations. So as I said, targeting natural waters like seawater, brackish groundwater, and brine from desalination plant is not viable for these elements like lithium and the low concentration one. So this was an important conclusion. I think now the scientific community aligning with it, and because if you go before, you see a lot of paper recovering of lithium from seawater. And again, I hear it even now that NEOM, they want to recover rubidium from brines. Again, I did not do the analysis for rubidium, but again, I'm not sure if it will be economical at all. So now we need to recover metals from wastewater and brines. Again, this is the conclusion. And there are plenty of wastewater and plenty of brines, including industrial wastewater like batteries and the battery facilities, semiconductor industry. The problem with the semiconductor industry that they will not tell you what's the composition of their wastewater because it's secret. But if you can get information, I don't know, through some kind of a spy that works in the company, you can figure out. But I don't know, I tried and I was not successful. We know that recovering of brine from the lithium triangle in Argentina, Bolivia, and Chile, it's quite viable. Again, there are plenty of lithium there. The concentration is huge. And again, you need to find some way to recover them better than what they do now by mostly evaporation ponds, which takes about more than 1 year to recover. Now, there are some conventional technologies that work not bad. I mean, for example, precipitation can recover, some metals like magnesium and calcium. You can recover it by precipitation, but they are very chemical intensive. Solvent extraction, is very, very common. And again, most of the technologies in China, they use solvent extraction. So now, we in academia say it's very chemical intensive, but it works quite well. But we need to do better. And also you can have ion exchange. Ion exchange also need a lot of chemical to recover it, but you can recover very well. And the industry developed very, very, very specific resins. There are amazing selectivity, including the solvent extraction. They developed some extracted molecules that they add ligands to the solvent extraction. They are very, very efficient, much more than you can see from any of the papers that we publish, including Science, Nature, etc. So we can have, instead of conventional technology, we can think about metal recovery by other, like electroabsorption or CDI. And you apply electric field, you have electrodes, and the certain ions, if it's cation, will go to the right electrode, and then you can just short circuit or reverse the polarity, and you can release it. And the mechanisms there can be either adsorption into the electric double layer, but again, this will not be selective. It can be just attracted by charge. Or you can have some intercalation materials, and these work very, very well. For example, lithium-ion battery have sort of like intercalation materials in which the lithium can intercalate very, very well. So this may be a process. We can also use membrane technologies, and I will focus mostly on membrane technologies. It can be pressure-driven, electric-driven. Concentration-driven will not be economically viable for technology, but again, it can be used for laboratory to study fundamentally the process. And the mechanism can be by sieving. And if you can create a membrane which is very, very accurate and precise pore size, which is very challenging, you can really separate by size or by chemical affinity. And I will talk about the chemical affinity when I talk about the potassium channel very soon. Now, let's talk about the type and difficulty of ion separation by membranes. The easiest one, again, this shows you the difficulty of extraction. The easiest one are opposite charge. We can just use ion exchange membranes in electrodialysis, and then the cations will go to the cation exchange membrane, anion to anion exchange membrane, and we can get very high selectivity. So this is not an issue there. But again, many times we don't want to, again, separate, for example, lithium from chloride. We want to separate lithium from sodium, and then it's become more difficult. The other one is different valency. If you have divalent and monovalent, we can use nanofiltration. And nanofiltration, again, if you perfect it, can do quite a good job between magnesium and lithium, for example. And the most challenging are the one with the same size and charge, again, like sodium and lithium, magnesium, and let's say copper and cobalt, and so on. So these are difficult because they are quite identical, and you need to have more sophisticated way to recover them. So let's start now to show you one example for the nanofiltration, and most of the example will be the more challenging one for the same size and charge. So let's talk about nanofiltration. It's very common to use nanofiltration for softening. You can remove divalent cations, and you can use it also, for example, magnesium and lithium separation, which is just the preliminary stage before further removing or separating the lithium. So the way we have a nanofiltration, we have interfacial polymerization between trimethyl chloride and piperazine, and it's a very uncontrolled reaction. So we can get a thin film that does the separation, but because it's uncontrolled reaction, we have a pore size distribution. It's not uniform pore size. So I'll show you some work that was done by Liang et al. Again, I was part of the team, and Xiong, Lin, and again, here for this IP, they used the same IP, but added sodium dodecyl sulfide to the aqueous phase. Again, when you do interfacial polymerization, you have aqueous phase and organic phase. And then the sodium dodecyl sulfide migrated to the interface of the water-oil interface, in which the tail was in the organic phase and the polar head here. And by doing so, again, if you read the paper, there's some details and proved by simulations, the interfacial polymerization was more controlled, and you were able to get more uniform pore size. We quantified the pore size. Now let's see what's the impact of this slight modification in the IP on the separation performance. In the top, and again, we call it surfactant assisted regulation of IP. On the top part, we see the rejection versus the size of the ions for the conventional nanofiltration without any modification. This is the way we do conversion membrane, and we see that the separation curve is not sharp, it's very diffuse. As opposed to the one that we do by surfactants, the method that I mentioned just before, surfactant assisted regulation of interfacial polymerization, when we control the pore size, because the pore size was more uniform, we see that we get a very sharp separation. So I tell you that, again, if you use nanofiltration and you do it right, you can create some membrane that can be very effective for separation of magnesium and lithium, which is very important for any step of lithium extraction. But this was relatively not as difficult, because as I told you, the most difficult are ions of the same charge. So let's talk about ions of the same charge and see what are the challenges and how we can improve them. The problem with the current membranes, again, most of the membranes, again, except the one that you see in the literature, the one that we really use are polymeric membranes. And polymeric membranes cannot distinguish between ions of similar size and charge, because the mechanism, again, is by size exclusion, but again, the polymeric membrane has a very wide distribution of pore size, and also by charge. Just simply by charge, by donor exclusion, it's not enough. Again, it's not, you cannot separate between lithium and sodium just by donor exclusion. So we need to find a better way, and again, we can go and see how biology or evolution does it. Again, the potassium channel was evolved over evolution of billions of years. It works very, very well. And we have it in all our bodies, even some plants, in many parts of our bodies, in the cells. And the potassium channel can distinguish between potassium and sodium very effectively. The selectivity of more than 1,000 for every few thousand of potassium that go through, only one sodium will leak through the membrane. And how it does it? It has again, it's a very thin membrane, if you can call it. Only 12 angstrom, 1.2 nanometer. We tell you that if you try to engineer it, in reality it's very, very difficult, very, very thin. And it's a very narrow pore size, the right size, and also the right functional groups. So what's happening there, when the potassium come here, the potassium is hydrated, and it's completely dehydrated. When it is completely dehydrated, it's unstable, but it binds to this oxygen-containing group, and now the lithium, the potassium feels exactly like there is some water molecules around it. As opposed to the sodium that doesn't fit in the size and cannot coordinate here, so it doesn't follow this mechanism. And once we have this potassium, it can move by diffusion, by the chemical potential, and there are some other mechanisms like knockout effect, and you get if you have one potassium here and one potassium here, because they're positively charged, they will push each other, and we get very, very, very nice selectivity. And again, the key here, the size, the complete dehydration, and the chemistry. So, and again, if you think about reverse osmosis membrane, they're also very, very small. In reverse osmosis membrane, lithium can dehydrate, but not completely, only partially, or the same thing with sodium. So what's happening if the sodium will be completely dehydrated? You will get zero rejection because the naked sodium ion is smaller than the pore size of the membrane. But here, because of the unique part, and I'll show you later in another membrane, the complete dehydration, this is why it goes very, very fast here. Now, we can take the principle of the potassium channel as a guiding principle for ion-ion selectivity. So if you want to design a good membrane, it should be a small pore size and uniform pore size so that the dehydrated ion can go through, but not the hydrated ions. So it cannot be too small, so the naked ion cannot go through. You need to have the right binding site, and I told you about the potassium channel, and again, the right binding sites, the right distance, and the right chemistry to bind to the ion, so the ion will feel now stable again, because you cannot just dehydrate the ion. If the ion naked, it's very, very unstable. So dynamically, you need something to grab on, and this is perfect. You need to have a thin layer, so you'll be reasonable flux, but not very thin. It's super, super thin, you will not get selectivity. And the potassium channel does it with only 1.2 nanometer. It's quite amazing. But again, it's evolution for a long time. And we need to have narrow spacing between the groups here. And this is what we call the knock-on effect, in which one potassium pushes the other potassium. And they move not only because of this mechanism, but also because of the chemical potential gradient along the channel. Okay. So again, I'll show you some work, again, not potassium channel, but try to design some principles following roughly the idea of the potassium channel. And here we created a membrane for a divalent cation separation. And I'll show you later mostly about transition metals like copper, nickel, cobalt, and zinc. And we selected, we created a polymer, anionic polymer, which has what we call the immunodiacetate. These are two carboxyl and nitrogen, which have very, very strong binding to divalent metals. And I'll show you some data soon. And this is just PAH, it's a positively charged polyelectrolyte, so we create layer by layer membrane. Now, unfortunately, this polymer is not available commercially, so we need to synthesize it by the method here, like a cooking recipe. And then we do layer by layer, positive, negative, positive, and end up with a negative one with this functionalized, highly selective, highly complex in functional groups. Now we selected the separation of divalent cations of similar size, cobalt, zinc, nickel, and copper. And as comparison also we put magnesium here. So the four metals that we are interested in are, again, quite relevant to batteries. So these are more like transition metals. And this magnesium is just as a comparison. And as you see, look at the scale here, they have roughly the same hydration energy and roughly the same size again. This is the ionic radius, or the naked ion radius in angstrom. So this will be quite difficult to separate, but I said let's try with this immunodiacetate. So first we need to study the binding of this immunodiacetate to these metals. So we do some DFT calculations for this binding of these immunodiacetate for magnesium, cobalt, zinc, nickel, and copper, and we see that the copper is the highest binding energy, and magnesium is the lowest binding energy. And this DFT calculation were roughly similar to what you can get from the stability constant of complex formation you can get from the literature. So now we know that you can have a binding here, and let's demonstrate selective binding. I mean, if this principle that I mentioned will work. So we took magnesium and copper, which are roughly the same size, but much different binding energy. We do experiment with a diffusion cell in which we create this membrane that I mentioned here, put it here. Here's the feed. We do it at low pH, so both of them will be, the copper will be copper 2+, and this is more like a DI water, so the thing will go by osmosis to here. And now I'll show you data with single salt experiments. Again, single salt experiments are not telling you anything about the selectivity for a mixture. But we see here that when you measure the concentration versus time, for copper, the concentration versus time, which is slope with the flux, is much lower than magnesium. Because copper, when you do single salt, bind more strongly to this immunodiacetate group, and it slows down. Okay? As opposed to magnesium doesn't bind. But the key here is to see what's happening when you have both of them together. And here I'll show you some of the hypotheses that we, I don't know if you can move this part here, but let's see if I click here, it will try to click it here. Can you remove this one? No. Okay, good. Okay, so we thought about these possibilities we have in nature. If the binding is very, very strong, we call it site inactivation. The copper will bind here, and then this functional group will not be able to be used in any separation. It will just be immobilized, and then all the rest will come here and you will not be selectivity, because once you saturate it, the copper will flow in, the magnesium will flow in, and you will not see a lot of selectivity. The other one is site hopping, more like the potassium channel. If the binding is not super strong, we hypothesize that the copper will bind and hop from side to side, and the magnesium will not be able to do it because it cannot fit here and doesn't have strong binding, and we will not see any separation. Okay, so let's see if this is valid again. This is the result I showed you earlier for single salt. And now when you do a mixture, surprise, we see this behavior. None of the magnesium, in a single salt experiment, magnesium flux was the highest. Now we barely can measure it. It didn't go at all, as opposed to the copper that followed this hypothesized mechanism of hopping from side to side. And we see that the selectivity was about over 60. So quite amazing, and we were, surprised, not surprised, whatever. So, but this is a good way that you think that if you have the right binding site, you can have high selectivity. But again, we use layer by layer membrane, so you cannot control the site will be the right distance. You cannot control the pore size. If you were able to do it in a uniform channels in a very, very controlled modification, then you can get high selectivity. Also, we found when we looked at selectivity, again, remember this is the binding energy of each of them. So we wanted to see, here I did copper and magnesium. Let's do what happened for nickel and magnesium, zinc and magnesium, and copper and magnesium. So here I present another way to normalize the selectivity again. This is the copper and magnesium that I showed you earlier, but again, we here define it slightly different. And this is copper and cobalt, copper and zinc, and copper and nickel. And what we see, again, this is the selectivity, and here is the binding energy difference. The difference between, again, copper and magnesium, the difference would be whatever, and you plot it here. If you took copper and zinc, you take copper and zinc, and you write the difference. And we see a very nice, again, correlation in which the selectivity correlates roughly with the difference in the binding energy. So it tells you that binding energy, if you tailor it correctly, and if you can synthesize membrane with very well-controlled binding sites, it would be a good way for separation. Now I would like to conclude with another method, and let's take some inspiration from the battery materials and see if you can use them for highly selective lithium separation. So we know that batteries, again, lithium-ion batteries, usually you have an electrolyte solution, organic solvent, and again, that serves as the electrolyte in which the lithium goes there. But it can be flammable, and you heard about some thing that caught fire. Can never happen to me. I've never had anyone like people. I didn't know that there was the iPhone, but you heard about the Boeing 787. I think when it just was launched, they had some issues with the batteries burning. So then a lot of research for the battery industry to move to what we call solid state electrolyte. Instead of liquid electrolyte, we use some solid state inorganic electrolyte in which the lithium can move here. And it's a very complex structure, again, of a polyhedra, very, very well connected crystalline, which include many metals, and again, you can dope them with some other germanium and so on. And very, very complex transport mechanism. And here, the lithium here moved as a, when you have the ion battery, as a just not hydrated, because there's no water there, just a naked lithium ion. But these materials were not explored. Again, there were maybe one or two papers, not very thorough, how we can use them for aqueous separation in which the lithium is hydrated and use the solid state electrolyte as a membrane. And we published this paper again in May, so about half a year ago. They talk about this separation, and I will give you some of the highlights. So we ask ourselves, can we first, before going to the solid state electrolyte, can electrodialysis be used to separate lithium from sodium, for example? And again, you know that when you have cation exchange membrane, it's not effective, but here we said let's use, instead of the cation exchange membrane that is not selective, let's use a solid state electrolyte that can be used as a cation exchange membrane. We put it here, and this is a typical operation of electrodialysis in the laboratory. You have a feed solution, the receiving solution, and you measure the depletion of the lithium here, or the moving of the lithium to the side. And here we use the commercial Nasicon-like materials that use in the battery industry. And again, it's a Nasicon-like because it's sort of like tailored to be also selective for lithium. And this is the chemical structure of this solid state electrolyte. And again, this is a typical electrodialysis they do in the laboratory, rinsing solutions, and then you put AEM in both sides of the rinsing solutions. So first, we wanted to check the initial selectivity of the lithium for single salt. So we just did single salt experiments. So when you have sodium chloride and magnesium chloride, and we changed the voltage, increase it, decrease it, nothing came out. So this solid state electrolyte in this electrodialysis process could not pass sodium or magnesium through the solid state electrolyte. However, when we did lithium chloride, we saw that above a certain voltage, we start to get, and as you increase the voltage, the current increases a lot, so you have a lot of lithium coming through by probably electromigration, and I'll talk more about the mechanism. So we can say that lithium is the only charge carrier, or the only one that can transport through this solid state electrolyte. But this is single salt, and of course we always need to know what that means in the mixture. So let's have a mixture in which you have 10 millimolar of lithium and 10 millimolar of sodium as a feed, and we see the same thing. Nothing is coming out through the, again, from the sodium. Nothing coming out for long hours. Again, we operated for a long time. We operated, I think it's 4 volts, and we get very nice separation of lithium, what you see here. So, and again, it passes, and again, concentration versus time, very, very fixed charge, flux. So we see here, no detectable ion flux. So again, although, you can call it infinite selectivity, but again, in the paper, we divided it by the detection limit of ICP-MS, and we got 7,000 selectivity. Nothing was detectable for the experiment. It took very, very, very long time. Now here I should mention that the lithium, to get inside, must be dehydrated, and then completely dehydrated, and then it can fit exactly in the size there and move there. So, and the reason I don't think here I will show it again. I gave in where I presented another seminar someplace again for the students in the IMSTEC, and I talked very, very more detail about this paper. But here I'm going to give you the outline. So what happens there when it's dehydrated, it immediately binds to all these oxygen and all this group that you have there, and it's going to feel compensated, and then it's very, very favorable, process. Now here we will have a size sieving mechanism, So what's happening here? If you look here, let's before going over that. So the mechanisms of lithium transport in a solid state electrolyte are two of them. One of them is by vacancy. If you have some vacancy, the lithium will just go from vacant side to another vacant side. And this is well known from the solid state diffusion and very well known from battery. And also you can have some interstitial, through the interstitials between the polymer, some transport can happen. And importantly, when you go from polyhedra to another one, and from octa to tetra, there is a small bottleneck. Again, you need to go through them. And the size of this bottleneck is very important, and this is what I'm going to show you here. This is showing the migration barrier, what's the difficulty to migrate versus the bottleneck size between, again, the connect between the polyhedra. And our solid state electrolyte is roughly similar to what you see here from this paper. So it's about a little over below 2. And if you look at lithium, lithium is 1.8 when it's dehydrated, so it can go through, but sodium, when it's dehydrated, is 2.2, so sodium cannot go through. So this is why. Now, by the way, also we did experiments here. We used draw solution. We did the like see if any water going through. So we put one side lithium chloride, the other side sucrose is a draw solution, and then we compared also to ion exchange membrane. For the ion exchange membrane, we saw water going through, but for this solid electrolyte, we did not see any water going through. And why? Look at the size here of the bottleneck, 1.8. And remember what the size of water molecule, 2.8. So it doesn't go through again. And again, I'm giving later tutorial solution diffusion mechanism. If the solution diffusion mechanism is correct, you'll see water going through, but no water, because you just saw it doesn't go through. And again, you can think about it, there's some very, very small pores here in which lithium can go through, but all the others are big enough, cannot go through. Also, we did also analyze the phenomenon that will be detrimental, and again, we need to overcome it if we want to use it for a real application of direct lithium extraction. We measure the lithium flux versus the molar ratio of the competing ion. M is the competing ion versus lithium. So the triangles are sodium and lithium. This is the ratio of sodium and lithium when you have a mixture. And the green circles are magnesium and lithium. And here, if it's ratio 1, it means you have the same molar ratio of sodium and lithium. Here, we have very little of the competing ions, sodium or magnesium, and much more of the lithium. And as you see, as you increase the concentration of the competing ion, as you move along here, the flux decreases. So, decreases significantly with sodium and with magnesium. So, still, we get perfect selectivity. The sodium and magnesium do not go through, but they reduce the flux of the lithium. And so again, what you see, lithium ion flux decline in the presence of competing ion cations. And why it's happening, we explain it. So what we think, and we verified by some molecular simulation, we took a very thin layer of the top, just the top layer of the solid state electrolyte, and did molecular simulation to see how lithium goes through. We apply electric field, non-equilibrium molecular dynamic simulations. If you have only lithium salt, this is the green one, it goes through, you see. If you have lithium and sodium, sodium is the yellow, the sodium just go to the first layer, first polyhedra, and then it cannot go through because, again, remember, there is a bottleneck that you need to go through, and it cannot go through. So the sodium got stuck here, and lithium going through. So what's happening here, when the sodium get there, it just occupies some potential partitioning sites, so the lithium cannot find many of these partitioning sites to get in, and this is why the flux decreases. And the same thing with lithium plus magnesium. With the magnesium, the same phenomenon. Magnesium, the orange, get only to the first layer, cannot move farther, and only the lithium go through. So this is a phenomenon that we need to overcome. And again, competing ions do not penetrate past the surface, and they interfere with the partitioning and further transport of the lithium ions. And we can also verify, again, we can do take some EDS mapping of cross-section of the solid state electrolyte after the experiment. And this is the solid state electrolyte, this is the top layer. Just when you don't have any sodium. And we see inside this is the composition of the solid state electrolyte. You have a lot of silica, germanium, oxygen. And when you look at the bottom, at the end of the experiment, we see the red one is the sodium. The red one was just accumulated in the top layer, as we speculated, and as we found by molecular simulations. And this interfered with the partitioning of the lithium, so the lithium cannot go over. So I think the solid state electrolyte is really, it's an amazing transport mechanism. In the paper we described the energy barrier and the mechanism, what's happening there. Again, complete selectivity. When you think about it, in terms of evolution, the potassium channel, again, it will be unlikely that in our body and cell we have some inorganic materials. Again, it's not compatible with the body. But here, just by engineering materials, you can even get selectivity higher than the potassium channel, so it's quite amazing. So this brings me to the last slide. Now, the question, will membranes really outperform conventional technologies? And here we need to be cautious. First, I don't envision any process that you have just one membrane process and you can get just direct lithium extraction. It will be part of many, many stages, as we do nowadays. And also, I think some of the limitations, we suggest different membranes nowadays, again, including solid state electrolyte and so on. But I think we need to do a comparative techno-economical analysis and LCA to compare it to some conventional technologies. And I think what the limiting factor will be for these highly selective membranes that follow the potassium channel, I think the fluxes will be very, very low. So in my opinion, again, what we think, in my opinion, still sophisticated way of absorption by very selective absorption that you can release it. For example, a layer hydroxide, that you can absorb and release them by some, not very, very intensive chemicals. It can be well. I think I know some process that you can take some of these double layer hydroxide, double hydroxide, whatever, LDH, and you can release them by just water sometimes. So again, I'm always trying to be skeptical and not give a lot of promise, but still it's an area for research. So to conclude, metal mining for industrial wastewaters and highly saline brines, like the cellar one in the triangle or Solvent Sea, or maybe even some of the oil and gas produced water, it can be viable, but not from seawater and desalination brines. There's some lot of research, and again, I'm skeptical also when NEOM project started in the one in Saudi Arabia. They claimed they want to recover everything. I think now they scale down and they say, oh, now we can go maybe for magnesium and again, I'm not sure about rubidium. They push now rubidium, and I suspect that it's not, concentration is not very high, but again, I did not do any analysis. So selectivity between nearly identical cations is possible with polymer membranes via coordination chemistry, but again, I think polymeric membranes will have a problem in the future to get very, very high selectivity, because it's very difficult to engineer polymeric membrane with very, very uniform pore size. But again, you can have, on the other hand, I can have maybe some kind of crystalline materials like MOF, COF, etc., which is very, very difficult to upscale. So, like any good chemical engineer, you can even take a polymeric membrane with selectivity of 20, and you know that chemical engineering, by staging, you can improve the selectivity. So just do staging, and you can get the right selectivity. And we need, as I mentioned, comparative TA, LCA analysis for membranes via versus conventional technologies like absorption and solvent extraction. So this brings me to the end. I'd like to thank many of the people who did the work, and again, this is some of my group at Yale that many of them moved to Rice. And thank you for your time.